force on a charged particle moving in a magnetic field. So when a charged particle enters perpendicularly in a uniform magnetic field, it experiences a force. This force is by nature centripetal. Centripetal means that it is a circular deflection. This force produces a circular deflection. Look at this field, magnetic field, and the charged particle is deflecting in the circle. Now we discussed that why this happens, that when a charged particle is moving, it produces its own magnetic field. The charged particle own magnetic field interacts with the external magnetic field, and this causes a reaction force. Now look at this screen and look at this diagram. And if you remember that we had done example 1, I think so, if I'm right.
Yes, sir, we're done with example 1.
And we mentioned that if the field is very strong, the charged particle will be turning in a circle. Now, I'm putting my first concept for today. A charged particle deflect in electric field. A charged particle deflect in a magnetic field. But in an electric field, the deflection is projectile. In a magnetic field, the deflection is circular. You have to copy this. The charged particle shows a deflection in electric field, in a magnetic field, but the deflection is circular in magnetic and projectile in electric. This is a contrast.
Done, sir.
Now, in cases here, air resistance is 0 and F is equal to mv squared will be applied here, and T is equal to 2 pi upon omega. These formulas are coming from chapter number 1. We have to copy this.
Done, sir.
Now, example number 2. Example number 2, a charged particle is entering in a magnetic field. A charged particle is entering in a magnetic field, but the charged particle is positive. A very important concept to remember, that the direction in which positive particle is moving is the direction of current. I repeat, the direction in which a positive particle is moving, the direction in which a positive particle is moving is the direction of motion. While when you are talking about negative particle, if it moves forward, the current would be backward. You have to copy this screen, this example.
Done.
Look at the deflection. The deflection is in the upward direction. The deflection is in the upward direction. This is according to Fleming's left-hand rule. If the current is in the right direction, magnetic field is in the page, and if you put the left-hand rule, you will get a direction which is upward. You have to update the same screen.
Done, sir.
Now, the negative particle is entering in a dot. Dot means out of page. Remember, the negative particle is moving to the right. If the negative particle is moving to the right, the motion of electron would be on left. You have to copy this example. I have shared with you the patterns, field patterns of a solenoid and a straight wire. The magnetic field chapter is quite a long chapter, and it deals with the multiple options like Fleming's left-hand rule, Fleming's right-hand rule. Now this negative particle enters, and according to Fleming's left-hand rule, according to Fleming's left-hand rule, the force will be upward. The force will be upward. Now you have to update the same screen.
Done.
So now you have to remember the direction of the force. Direction of the force is determined by Fleming's left-hand rule. Now, this is a phenomena of a charged particle. When it goes through a neutral region, it won't deflect in any direction. It goes straight. But now look at this screen. See the deflection. The charged particle is deflecting in a very straight line. Oh, sorry, very circular path. Charged particle is deflecting in a circular path. Now, how you can memorize it? This is the diagram to memorize it. In a cross, cross means in the page. Cross field, positive bend upward and negative bend downward. If you put it dot here, these two positions will be reversed. This is a way to remember it. Now, formula. We have to remember that the force on a charged particle experienced by a charged particle depends upon some factors like quantity of charge, velocity, magnetic field strength, and angle. Now you have to copy this. Formula is the force, quantity of charge, velocity, magnetic field strength, theta. The arrow means it's a vector quantity.
Done, sir.
I've shared with you the diagrams for the support. Actually, this topic needs good understanding, good visualization. And hopefully when you watch these videos and you watch that the quick small positions like the diagrams, it will really help you that actually when left-hand rule is applied, it's a way to locate the direction of the force. But left-hand rule itself, not a justification of the force. Why the force is applied? It is due to interaction between the field, magnetic field present and the magnetic field due to current. Case number one, charge is at rest. It's a very important concept. Velocity is zero. If I put zero in the formula, I will get 0 Newton force. Theoretically, why this happens? When the charged particle is not moving, when the charged particle is not moving, it won't produce any magnetic field. It will actually produce an electric field. So no interaction, no force. This is to copy. I'm just coming, copy this screen. Case number 2. When theta is 0 degree in the formula, sine 0 is 0. So the formula will be F is equal to 0 Newton. When theta is equal to 90, force will be maximum in A2. Every concept has a physical explanation and a mathematical explanation. Mathematical explanation is always simple. Sine 90, sine 0 are values, so we can use it we can directly put the values. So now copy this screen. तो आप देख You have to copy this screen. Let me know once you have copied it.
Done, sir.
Now look at look at the part 3 of case number 2. If theta is not 90, when theta is 90, the deflection is circular. But if theta is not 90, the deflection will be spiral. It will be like a solenoid forming in vacuum. So this is a special case when theta is neither 0, it is not 90, it is like 30, 40, 60. The deflection will be spiral. You have to copy this.
Done, sir.
So there is a deflection difference. Now, when a charged particle enters at an angle other than 90, the deflection will be the deflection will be not 90-degree, sorry, not circular. It will be a deflection in a spiral form. This animation shows how it appears. This red dot is the charged particle and it's moving in a magnetic field. It is being deflected in a circular path. Look at the shape of the pathway of the diagram. It's moving now. This is called top view. And now this is called front view. This is called top view. This is called top view. And in this way, the charged particle can be deflected. Look at this animation again. The deflection is circular. Now, case number 3. Change in velocity. Formula says F is equal to QVB. So force is directly proportional to velocity. So when a beam of charged particle enters, which contain particles of different velocities, the faster particles, according to the formula, will experience more force. So they will deflect more. The slower particles will experience less force. So they will go in a bigger radius. So these are, for example, beta particles is a case here. So this is a special case. It means faster particles get more deflection than slower particles in a magnetic field. They're entering perpendicularly. You have to copy this screen. And I'm just copy this screen. Faster charged particle, stronger electromagnetic field. So greater interaction with the resident field and it means greater force, greater deflection. You have to copy this screen.
Done, sir.
Case number 4. F is equal to QVB. So if I keep other variable constant, force and magnetic field strength are proportional. Theta is 90. This is the 90-degree case, so it means force will be maximum. In a stronger field, charged particle will not escape. It will be bound inside the field. Otherwise, it will escape in a path and then goes straight after that. You have to copy this.
Done, sir.
If the field is very wide in a very big region, even a weaker field can produce a complete circle in deflection. Now, that concept comes again. Force, magnetic field, and velocity are mutually perpendicular. Force acting on a charged particle in a uniform magnetic field is centripetal in nature if the charged particle has entered in a at 90 degree. So you have to copy this screen.
Done, sir.
Now look at this. The velocity is perpendicular in direction. Now, this is a concept, if you remember, our first chapter, circular motion, is coming from there. The arrow of velocity is perpendicular to the perpendicular to the centripetal force. What is omega? Omega is called angular velocity, and other letters are known. Theta is called angular displacement. Now you have to copy this memory lane.
Done, sir.
Give us side heading derivation. This is a very important derivation, and this is the most important derivation in this chapter. Just like in gravitation, you must have seen Kepler's law is derivation is their favorite. The derivation is based upon the idea that in the magnetic field, the centripetal force is coming for magnetic field, that it's originating from there. You have to copy this screen.
Done, sir.
Now, Q upon M is equal to charge to mass ratio. It's a new thing to remember. Coulomb per kg, and the charge of electron was later known. So they were able to even find the mass of the electron. You have to copy this. Now, if you have copied this, now give a heading, second derivation. Look at the diagram again. Magnetic field is centripetal, providing centripetal force. You must remember that it is the formula mr omega square. There are two formulas in this article. There are two formulas in this article. One is F is equal to mv square upon r, and one is F is equal to mv square upon r, and one is F is equal to mr omega square. Now you have to copy this derivation.
Done, sir.
Now you have to remember that what was the equation for time period? What was the formula for omega? Omega is equal to 2 pi upon t. If we replace it, we get a formula for capital T.
Done, sir.
Now give a heading, second unit and second definition of B.
Done, sir.
Formula F is equal to QVB sine theta. First, I have taken theta is equal to 90. Sine 90 is 1. Sine 90 is 1. So I have used that sine 90. I have used that sine 90 and I got a new formula for B. Theoretically, this is the third formula for B. You have to copy this.
Done, sir.
Now, formula is F is equal to QVB. So B is equal to F upon QV. So we can make a definition for magnetic field strength from here. You have to copy this screen.
Done.
So when you say B is equal to F upon QV, you can define it from this formula. Magnetic field strength is, F upon Q. Magnetic field strength is the force magnetic field strength is the force on a charge per unit charge and per unit velocity provided the charge is moving magnetic field. Now, this is the second definition. The first was related with the formula BIL sine theta. So you have to copy this second definition.
Done.
Whenever whenever you want to define a physical quantity, you should always try to make a definition. You always should try to make a definition by using the idea of 111, which is called the unitary method. You make every quantity, you bring every quantity to 1 and then you define it. Now you have to copy this screen.
Done, sir.
Now, you need to make a story from this equation, which is possible to make a definition for Tesla. So remember, the story is always simple. It always has to connect the points. So you will say, for example, one Tesla is the strength of a uniform magnetic field. One Tesla is the strength of a uniform magnetic field which can exert a force of 1 Newton on 1 Coulomb charge moving at 1 meter per second at right angle to the field. This is the definition. This is the definition for Tesla.
Done, sir.
Now, behavior of charged particle in electric and magnetic field. When a charged particle enters an electric field, it experiences a force which is parallel to the field. This was in our AS and it was in A2 also when we were doing E-field chapter. Look at this screen and the arrows are upward and the force on the charged particle is downward because the charged particle is negative. Deflection is projectile. When a charged particle enters a magnetic field, it experiences a force which is perpendicular to the field. Here it is a circular deflection. So E field, the force is parallel to the field. The formula is QE. In B field, the force is QVB sine theta. When the particle is at rest, it won't experience any proper force. Now, this is actually in our memory, the thing is available, but in A2 physics is like this. It actually collects known facts and keep on revising them, keep on repeating them. This is how A2 works. So you will see many things repeatedly coming. So this is their pattern of asking the question. So we just have to give this heading first. You have to give this heading.
Done, sir.
So let's keep it up to here. And we will inshallah continue this in our next class. Allah Hafiz.
Thank you, sir. Allah Hafiz.